Okay, everybody, welcome back. A couple of things. One, I sent an email reminding you about what you have with respect to tutoring. If you need tutoring, please do get it with tutoring help as soon as you possible. Please don't wait until toward the end of the semester. Okay. Also, there were two professors from GCC who were doing study sessions. You're still doing it, so I gave you the link and information how to get to it. So then, second of all, I don't have technically, I'm told that as adjunct, we're not required to have office hours, but if you need some assistance and you can't get those other resources, send me an email and see what we can do. I could probably spare some time in between my classes. Okay. All right. So, and finally, don't forget Tuesday is the next exam. Similar format as all the other ones. 75 minutes and over chapter 7, 8, and 9. Okay, so let us finish up chapter 9. And yes, again, we'll be here Tuesday. If there are no questions concerning the exam, I will continue with the next chapter. All right, any questions? No? All right, well, let me start this screen, and we ended up on slide number 7. Okay, now, in this chapter, we're talking about acids and bases. And remember, we had two definitions of acids. We had the Arrhenius definition, which is that any chemical, any compound that when put in solution, an aqueous solution, a water solution, produces a proton. And if a proton is produced, that is classified as an acid. For the Brownstedt-Lowry definition, similar definition, it's producing a proton. So that's a definition for that, for an acid in both different explanations. The base is a little bit different. The bases are for Arrhenius base is just simply a chemical that produces a hydroxide ion. That is a polyatomic ion, OH negative. And where they differ with respect to Brownstedt-Lowry is just that, the base. And for Brownstedt-Lowry, a base is any chemical that will accept that proton. And that allowed the definition of a base to be expanded to include other compounds that had nothing to do with hydroxide. Okay. Now, when we talk about strong acids, strong bases, I think when we talk about electrolytes in general, and the term, I use the electrolytes in this manner. We're all familiar with the term electrolytes, or you should be, maybe because out there you can go buy a bottle of electrolytes. And all an electrolyte is simply an element that has either lost or gained an electron. It's an ion, okay? Now, some chemicals, when they are dissolved in the water solution, are very strong electrolytes because they dissociate completely. They break up. Water has strong enough solvating capabilities that it breaks up the molecule into ions. Now we have what are called strong acids and strong bases. A strong acid is nothing more than an acid, which is a covalent compound, that will dissociate 100%, approximately 100%. That means that if I had 100 units of let's say, let me give you an example. If I had 100 units of, get my pen to work here. One second. Okay. Am I going? Okay, so let's say if I had 100 units of hydrochloric acid molecule, hydrochloric acid, 100 of them, right? They dissociate. Well, when they dissociate, being it's a strong acid, it will give me 100 units of the proton and 100 units of the chloride ion. Okay, approximately 100, approximately 100%. Now you might think, well, wait a minute, how's that work? Well, think of it this way. Think of this HCl as a unicycle. Okay? What do I mean by, how does that relate? Well, a unicycle has a frame and a tire, right? One tire. Well, when I take the tire off, do I not get 100 tires and 100 frames? Yeah. So hydrochloric acid, being a binary acid, when it dissociates, gives you 100 units of the proton and 100 units of the chloride. Okay, 100%. The same is true for the base, strong base. Sodium chloride, we're going to learn here with solubility rules. The fact that you see sodium tells you that it is soluble. The fact that it's classified as soluble, it will go dissociate roughly 100%. So the same scenario, similar scenarios here. If I have 100 units of sodium hydroxide, units or compounds, 100 unit molecules, I should say, 100 of them. Well, when they break up, I'm going to get 100 of the sodium ion and 100 of the hydroxide ion. Okay, 100%. So that is why we are talking about strong acid, strong base, because they completely dissociate. Okay, completely dissociate. Now we have hydrochloric acid, which is what's in your stomach, very strong acid, completely dissociates. We have HNO3, which is nitric acid, also very strong acid. And then we got this last one here called sulfuric acid. Notice here that it has two hydrogens. And what happens with that, I'm going to write that equation out. H2SO4, when it dissociates, it has two protons. You notice that? So it will generate two protons plus the sulfate ion. Doesn't that sulfate ion look familiar? SO4 -2. It's one of the polyatomic ions. A lot of those polyatomic ions are started off as acids, and then the proton was removed. Okay, so if we have 100 units of sulfuric acid, we're going to get 200 units of the proton and 100 units of the sulfate. Analogous would be a bicycle. Okay, HCl is a unicycle. H2SO4, sulfuric acid, would be the bicycle. A frame, two tires. I have 100 bicycles. I take off all the tires. I'm going to have 100 frames and 200 tires, right? That, ladies and gentlemen, is what we call a stoichiometry, something we're going to learn about. That's called the ratio, very important number up front, coefficient. All right, so these are our examples of strong acids, strong base, completely dissociate, 100%. Now, how do we write that? How do we demonstrate or show a diagram of that? Well, we had these beaker diagrams, okay? And what this is supposed to represent is taking hydrochloric acid and dissolving it in a beaker of water. Now, we know, I just told you that hydrochloric acid is strong. So when it is strong, it's going to dissociate completely into the ions. So to demonstrate or to depict a strong acid via a diagram, we would take, I don't know, 3 or 4 pairs of HCl. Pairs meaning I got 3 chlorides and 3 protons, okay? Make sure when you draw the diagram that you have the charges and you have an equal amount of the proton and the corresponding anion, okay? Totally dissociated, nobody's combined. Okay. Now, if we demonstrate one for a strong base, because we know sodium hydroxide is same base, similar situation. This is a strong acid, and this would be a strong base. And again, you can show, 3 or 4 individual ions. So in this case here, we got 3 hydroxides. And of course, we're going to have the corresponding cation, 3 protons. Wholly dissociated, none of them are combined. Okay, and now what do I mean by combined? Well, the next few slides will demonstrate this. This is a representation of a strong acid and a strong base. Okay, so there's 3 of them that we're giving you right now. The first one, HCl, is hydrochloric acid. I mentioned nitric acid, and then sulfuric acid. Okay, sulfuric acid has 2 protons that are generated when you dissolve that in water. 2 of the strong bases are sodium hydroxide and potassium hydroxide. In fact, there are more strong bases, and the reason they're called strong bases, we're going to learn here in this chapter, is because the fact that these ionic compounds are soluble in water, as defined by the solubility rules. And in the periodic table on the right side, bottom right side, there is a table that we're going to go over, and that is called solubility rules. Okay, and when molecules are classified as soluble, they dissociate 100%. They're very strong electrolytes because they dissociate so much. Also, when compounds are classified as insoluble, are you going to have either soluble or insoluble? They are classified as insoluble, so the majority of the material still remains intact. The ions still remain intact, but even though they're classified as insoluble, the fact that they're ionic compounds, there are at least one set, when we show them in the diagram, of ions in solution. Okay, because even though they're classified as insoluble in water, there's always a few of the ions in solution. They're weak electrolytes, which are governed by their solubility. Okay, and so here, what strong again means is the fact that they completely dissociate into their corresponding ions. Acids have the proton and the corresponding anion. And the bases, which are all ionic compounds, are just broken up into the cation and the anions, okay? And we do have what are called weak acids and weak bases. Some examples of a weak acid is HF, or hydrofluoric acid. If you ever did any staining of glass, as a hobby, this is probably what you utilize, called hydrofluoric acid. Reacts with glass be pretty good. So I'll have the names here in a bit in the table. The next one is H2CO3, is carbonic acid. Okay, notice the CO3. The CO3, does that look familiar? -2, carbonate. Okay, called carbonic acid. This one you may not be too familiar with, but that is a weak acid called acetic acid, aka vinegar. And also in your polyatomic ion tables, you will find this ion called the acetate ion. This was called the carbonate ion. And notice, remember earlier we had the nitrate ion, right? When we put the protons back on, they get converted back to their acids. And then this one, the final one, is called, you drink a lot of soda pop, phosphoric acid. Note the PO4 -3, isn't that, remember in the polyatomic ion table, the phosphate ion, okay? Phosphate. Now you can see that phosphate, acetate, carbonate, when you put the hydrogens back on, you put them up front like it's written right here. You take off the 8 and you add IC and the word acid. And so you have carbonic acid, acetic acid, phosphoric acid, okay? Now what's happening here is the fact that they are weak, meaning that yes, they render solubility, but not a lot. Okay, not compared to the strong acids. So what ends up happening is we have a double arrow, which means this reaction goes forward and backwards. But there's an equilibrium here, and it's favored, because it's a weak, it's favored the intact formula. Okay, there's a little bit as a proton and a little bit as the acetate ion. You know, and if, let's say I started off, let's say with 100 in the beginning, I got 100 molecules of the acetate, and I got 0 and 0 to begin with. And what may happen is this: after you dump it in water, you may now have like 95 of acetate, and about, you know, maybe less than 5 each of the proton and the acetate. Okay, because only a little bit went and broke apart, and it varies, but any from 1 to 5% of the acid is totally ionized. Okay, now how do we show that? Oh, the base, excuse me, the same way. Here's a typical base. You may be familiar with this. This is also milk of magnesium hydroxide. It has a double arrow. Okay, the fact that it's double arrow, the majority of it is still intact in the formula, and it's insoluble. So we show that with the physical state of S being solid. Now we still have a little bit of ions in solution, not a lot, but a little bit. Okay, notice that we got 2 hydroxides. Why? Because we got 2 hydroxides to begin with. This is analogous to the bicycle example. 1 frame, 2 tires. Okay, dissociates. I'm going to end up with 1 frame and 2 tires. Now HF, which was the weak acid, we show that in the diagram of water aqueous solution by keeping the HF intact. That demonstrates that the majority of it is still intact and together. And you can just need to show just like 1 pair of ions. Okay, that is, notice how this is different from the strong acid and base example where it's totally dissociate. Here we got to show at least 1 pair. The magnesium hydroxide is similar in that majority of it is shown here at the bottom of the container, still intact and is in solid form. That represents something that's solid. We have to show at least 1 set of ions. Okay, so this diagram here depicts a weak electrolyte / weak base because the hydroxide that is formed. Okay, so that's how we demonstrate graphically or depict a strong acid or base and a weak acid or base. All right, so here are the weak acids we gave you: hydrofluoric acid, carbonic acid, phosphoric acid, and acetic acid. Okay, notice that when these dissociate, though weakly, these are the respective ions, 2 protons. Hold on. Next one has 2 protons plus the carbonate ion. And then this one has 3 protons plus the phosphate ion. And then this one has 1 proton plus the acetate. Okay. And then here we show, because this is weak, the majority of it is going in that direction. We have a little bit of the ion and hydroxide. Excuse me. Okay. So these are examples of weak acids and weak base. Okay, simply because they do not dissociate 100%. Now let's take a look at these diagrams. So you got here a generic chemical in solution, HA can be anything, but you notice that it must be an acid of some sort because we got H plus. All right, so we can see that based on the diagrams, the strong acid will be shown by A, right? Everybody see that? Because literally all of the HA has been totally dissociated, 100%. So that depicts a strong acid, which means that B and C are most definitely weak acids because the majority of the formulas are put together, still maintained separately. We do have some ions here. There's one pair, another pair. This one's got one pair, and that's it. So these two, B and C, are definitely the weak acid. Okay. Now, if I needed to compare just B and C, can I make the comparison? Can I determine which one would be the stronger acid just between B and C? What could I do? What could I use to help me out to determine which one? Let me clear it. Which one would be the stronger acid, B or C? What would you guys say? Okay. We already established that A is the strongest acid of all the examples here. And we established that B and C are both weak acids. But can we determine which one is stronger within the weak acids, B or C? What would you say? Any ideas? Sure. Well, if you notice B, we have 2 protons relative to C that only has 1. So that suggests that B is a little bit stronger than C. Both of them are weak, but because B has a little bit more of protons in solution, that makes it a little bit stronger relative to C, okay? And so we have a range of acidity, and we're going to learn that here when we talk about the pH range. And then the strong base, well, there's nothing here. There's a strong base because there's no hydroxide being created, okay? All right, when D basically is some covalent compound because they're not dissociated at all, okay? Remember, the covalent compounds, when placed in water, do not dissociate. They remain intact. The only exception are acids. Acids are covalent compounds, but the nature of the beast is that those protons get easily removed with water to form an acid solution. Okay, which brings us to the pH scale. The pH scale is nothing more than a numerical value based on the concentration of the proton. All right, and that scale runs from 0 to 14. 7 is what is considered to be neutral. You might be familiar with this pH scale. If you have you got fish at home, you know, you gotta attend to the pH of the water and so forth. You have a little solution that you're checking the pH of it. You may have swimming pool, same thing. Okay, it's a measure of the acidity concentration. So 0 is extremely strong on one end, and the far right is 14, which is extremely basic. Now I'm going to introduce you to a notation which consists of brackets. If you notice here, I got the proton in brackets. That's a concentration unit that we call molarity, M-O-L-A-R. Now we're going to get to that in detail at a later chapter. For right now, it just says it's a concentration factor, is denoted by the letter capital M, and it does have units called moles per liter. We will come back to moles quite often when we get to the latter chapters, okay? All right, so what this is telling me is this, the way I read in the far left where I circled over here, it just says that the concentration of the protons is greater than the concentration than the hydroxide. The result is it makes a solution acidic. And note there's a range of acidity from 0 to just less than 7. With 1 and 2, pretty strong, 3 to 5, kind of weakly acidic. There's a range, okay? There's a range of them. Now, at such point in time that a proton concentration is the same as a hydroxide concentration, that is neutral, okay? That is neutral. And so from 7 on down is acidic, and that's what this relationship is. Okay, and when the concentration of the base, the sodium hydroxide, is greater than the proton, we are in what's called a basic solution. It's a basic solution or a alkaline solution. It's another name they use, either acidic or alkaline. Okay, pretty strong stuff up in here, and we'll get back to this. We'll come back to this here in a bit. As I stated, pH is simply nothing more than a numerical bed, okay? And this is a rehash of what I just explained about the concentration being the same or less. And either it's acidic in nature or basic in nature. You can use the term alkaline, that's fine, okay? And the brackets are molarity or they have units of moles per liter, but much more on that when we get back. Now, how do we calculate this? Well, we take the concentration of the proton and we take the log of that number, okay? If we take the log of that number, we're going to end up with a negative number. But you notice up here is the negative log. So to get the pH of, let's say, 1.01 times 10 to the negative 1 concentration, if that is pushed in there, because in your calculator you have a log button allergy, the value that you get is a negative 1. And you're multiplying it by a negative number, so your number is a positive 1, okay? Or 10 to the negative 1 concentration. Now, the numbers we're going to be using are pretty straightforward. In fact, you can use the exponent to help you out to figure out the concentration, but sometimes it's not always a nice even sequence of values, but we keep it this way here to demonstrate how that pH is calculated. So if we take something that's 10 to the negative 5, notice the concentration is getting smaller, all right? That is, you take the log of that becomes a negative 5 times a negative gives you a positive 5. Notice the concentration of the proton got smaller and the pH is going up in value to 5 into the weakly acidic condition, okay? This, if you take the concentration of the proton, which is 10 to the negative 8, that again is negative 8 times negative gives you positive 8. So again, the concentration of the proton is getting smaller, pH value goes up. That's inversely proportional, if you will. Concentration goes down, pH goes up for the proton. 10 to the third is a pH value of 3. Okay, notice that the concentration gets a little bit stronger, so the pH drops. And then you can either take the 10 to the negative third and see that, take the exponent, so negative third times negative, you got 3, or convert it to decimal values, so 0.001, which is the same as 10 to the negative third, you get You can plug that number at 0.001, plug it in your calculator, hit the log button. Okay, it's labeled L or G. Sometimes the log button is the primary button, sometimes it's a secondary function. So you can try that. All right, and then this one here, you can type that whole number in there or realize that that is 10 to the negative 8, which says pH is 8. Okay, so that's how we calculate the pH. Now we can start with pH and work backwards. Okay, and the way we do that is you take your pH and put a negative to it. And then take your calculator and raise 10 to whatever negative pH value it is. Okay, and so let's say you had a pH of 5, and so 10 to the negative 5. So that's the concentration of the proton, 1 times 10 to the negative 5. Some ideas about give you some reference points as far as pH and how acidic things are. Environment, pH roughly 2, maybe less. It all depends on each individual, and of course it's going to be very acidic because your stomach is just loaded with hydrochloric acid. And that's why it burns when it comes up your esophagus, because the tissues in the esophagus are not made like the tissues in your stomach that help protect the inside of your stomach. Your esophagus does not have the same type of protection. That's why it burns. Lemon juice around 2, coffee, varies on the brand, about 5. Saliva, again, depends on what you're drinking and your metabolic system, approximately neutral. Blood, very important, pH, 7.4. Your body's always striving to maintain that pH. Milk and magnesia, we believe is magnesium hydroxide. Its pH is quite alkaline, okay? Ammonia, 11.7. Urine, again, depending on individual and, what you're ingesting, around 6. Most of the drinks, soda drinks, colas, 2.5, around 3.5. Root beer, a lot is acidic. So if you think you might do better with less acidic soda pops, you might give root beer a chance. Which brings me to the point, you always hear about, okay, you're drinking too much acid, it's going to ruin your stomach. Okay, I want you to think about this and make your own decision here. Okay, your pH of your stomach is somewhere in that neighborhood, 1 to 2. It's very acidic. You're drinking sodas between pH 2 to 3. It's a little bit less concentrated. So are you really adding to your acid content in your stomach? Yeah, give it some thought. Okay, it's probably the other components that may be giving you challenges. The other aspect too is this, which is important, okay, is this. When an acid, remember the neutralization reaction, when an acid reacts with the base, the hydroxide, you always get water. That's why it's called a neutralization reaction, okay? Here's your acid, here's your base. That's why you take milk and magnesia if you got a little upset stomach, or you take Tums. Tums is a base, milk and magnesia is a base, reacts with your acid in your stomach, neutralizes it, converts it to water, okay? Now, out in the market, again, you make your own decision here. You have alkaline water. Now you know what they're talking about if you didn't know what it meant, but alkaline water has a higher pH greater than 7, somewhere about 8, 9 possibly, I believe, somewhere in that ballpark. Well, that's the base. You drink it and it reacts with your stomach, which is an acid. So guess what's happening? This reaction is happening. So whatever benefit the alkaline water came into play, you drank it, it got neutralized as far as it being basic. And what's left are the salts, which may or may not benefit you. So, I know I hear a lot about the benefits of alkaline water, but from a chemical perspective, the alkaline water, unless there's something out there I'm not familiar with, the alkalinity of the water gets neutralized as soon as it hits your stomach, okay? Also, a lot of stuff, I see a lot of bottles. And the reason I'm interested in that, and this is because when I was a graduate student, in fact, I finished my undergraduate school, and my undergraduate advisor wanted me to research some bottled water, because bottled water was coming up. And this is way back in the 80s, people were buying more and more bottled water, but they forgot that these bottled waters were loaded with ions, which is not good if you got blood pressure problems and so forth. So we did a lot of studies, checked the pH, checked for different ions, and we also checked for organic molecules, which are contaminants that are out in the environment. And a lot of the bottled waters were pretty much contaminated with organic compounds, so they weren't as pure as they advertised it to be. And then I read some of the bottles now, and I read the labels. They tell me DI water. What that means is deionized water. And what you do is you take ordinary water, you may distill it. You put it in a still, heat it up. It goes through a condenser, vaporizes, and then condenses, and then you got fairly pure water. And then they add magnesium and maybe some sodium and some other salts to give it flavor. And I'm thinking, whoa, really? Then they charge you an arm and a leg. And I'm thinking, you can do the same. You go to Fry's, buy a gallon of DI water. You go to the pharmacy department and you look for potassium, magnesium, chop it up, add a little bit to your water to taste, and you're good to go. And you saved a lot of money. So, chemistry. All right, where am I at? So the common pH materials. So let me see here. Buffers. Now, buffers are the only takeaway here about buffers are they are compounds that we put together so that they maintain a specific pH value, maintain it constant. Okay, and so it is made up of base and acid material. So when an external acid comes in, the base part reacts with it. When an external base comes in, the acid part reacts with it and helps maintain a constant pH. So they're very important, especially in blood. You have a pH buffer going on in your blood system because you're trying to maintain that pH 7.4. Okay, very important to maintain that. All right, so we have a chemical reaction here. This is a neutralization reaction. You have, if you analyze this and you break it down, first thing you should notice, I hope, you got hydrogen and then followed by NO3. That should flag you and say, I got an acid. Okay, so I got an acid sitting right here, specifically nitric acid. Then the other thing, you look at the other reactant, and we got calcium, and then in parentheses we have the OH, polyatomic ion, aka hydroxide, which is a base. Okay. Now, the other takeaway is this: the hydroxide, there are two of them, and this is a neutralization reaction. Earlier, I gave you the reaction of one proton plus one hydroxide react to give you one water. That is the relationship between the base and the acid. One proton, one hydroxide, one water. So if I have two hydroxides, guess what? I'm going to need two protons coming from the nitric acid to neutralize each other. And if I have two protons and two hydroxides, guess what? I'm going to make two waters. All right. Another way to look at this is if I have 100 protons, I need 100 hydroxides to give me 100 waters. If I have 1 billion protons, I need 1 billion hydroxides to give me 1 billion waters. Okay. So it's 1 billion or just 1 to 1. This is real important thing to remember because we're going to be talking about balancing chemical reactions. In other words, if I start off with 10 hydrogens in my reactants, I need to end up with 10 hydrogens as my products. And for this particular case, if we follow the protons and the hydroxides, we automatically balance the waters, and the corresponding salts just fall in place, okay? And we have a balanced chemical reaction, okay? So you think about this balance. I got 2 hydrogens total here, 2 hydrogens total here, for instance. I got 4 hydrogens on the reactant side. On the product side, guess what? I got 4 hydrogens on the product side in the form of water. Those are balanced. We have not violated the laws of conservation of matter. Okay. So here to ask you, which one of this is the Arrhenius acid? And I already identified what the acid was. And then the base, they're talking about the Arrhenius base because now we're dealing with hydroxide. If there was no hydroxide up there, it would not be an Arrhenius base up there. It would be a Brownstein-Lowry base, but not a Arrhenius base. Why does calcium bond to 2 nitrates? Well, obviously because the nitrates each have a -1, right? And the calcium is a group 2 element, and it has a +2 charge. So it will, oxidation number that is, it requires 2 nitrates because there are, each nitrate's a -1. All right, so we have these chemical compounds. And so what's asking us here is to draw pictures of them. Well, in order to draw anything, any pictures of what they are in solution, that's what's being meant here. Putting everything in solution, how do we depict a diagram? Well, to do that, we first have to define whether they're weak or strong, okay? And we know, because we gave you this, that nitric acid is a strong acid. Guess what that means? 100% this being dissolved. HF is one of the weak acids. And so only 1 to 5% of this is dissociated. Potassium hydroxide we gave you is a strong base. And we're going to learn why it's a strong base is because its solubility rules tell us that it's soluble. This means it's going to dissociate 100%. And then we looked at magnesium hydroxide, and this one was a weak base. Okay, we just gave it to you, but you're going to be able to figure it out that using the solubility rules, that magnesium hydroxide is essentially insoluble. If it's classified as insoluble, then it is a weak base. Okay. Potassium hydroxide is classified as soluble, which tells you it's a strong base. So we have to define whether it's weak, strong, before we can go any further. Once we do that, okay, then we define the ions that are going to be created, and nitric acid will give us the proton and the nitrate ion, okay? We define HF as weak, so we draw the double arrow. And so it will have the proton plus the fluoride ion, okay? Potassium hydroxide is defined as strong, so we have a one-way arrow, 100%, all potassium, all hydroxide. And magnesium hydroxide we defined as weak, so we have the double arrow. But we have to show some ions. So the ions are magnesium plus 2 hydroxides, okay? And so for the weak ones, we just show 1 pair of the corresponding ions. That's all we need to do. But we need to first identify strong or weak, then identify the ions, and then from there, go on to the next page. So we go, well, we have nitric acid, which was strong, and you can put 3 or 4 pair of ions in here. Don't forget the charge on each one for the corresponding cation and anion. Okay, it would be incorrect to just put H or just put NO3 because it is NO3 negative, not nitrogen trioxide. HF was weak, okay, and So we show at least one pair of ion, one proton, one fluoride, and the rest we can show 3 or 4 HF combined, not separated. Okay, that depicts a weak acid. Potassium hydroxide, strong, and so again we can put 3 or 4 pair of the corresponding ions. And then we have magnesium hydroxide, which is a insoluble. Okay, and so we demonstrate that we need to show at least one pair, one set of ions. Okay, and then the bulk of it is down at the bottom, together combined. Magnesium hydroxide still solid. And so if this was a beaker you're holding up, it would be a lot of the solid will be down at the bottom. Good example would be milk of magnesia. If you were to look at milk of magnesia, let it sit there, solid will come down to the bottom and settle. Okay, because most of it is insoluble. You got to shake it up to make an emulsion so you can swallow it. We're going to learn why magnesium hydroxide is insoluble, or determine that it is insoluble, because we're going to look at the solubility rules written down here and look at this, number 10. All hydroxides are in this insoluble table column. There's 2 columns, left and right, which means that anything that is bonded to hydroxide is insoluble, with a few exceptions, and we'll go into that here in a bit. But magnesium hydroxide is not one of those exceptions, so it is insoluble. Okay, so summarize all this. We got the Arrhenius acids, they produce a proton in water. The bases produce a hydroxide. When we talk about Brownstein-Lowry, by definition, there's a compound that loses a proton. Loses or to me, it's the same thing. You eventually have a proton in solution somewhere. Where they differ is the definition of a base, because the Brownstein-Lowry defines it as a base as any chemical that accepts that proton, and it doesn't have to be a hydroxide ion. Okay. Strong acids dissociate, ionize. Ionize, dissociate, same thing. They break apart 100% approximately, whereas the weak ones much less. Most of it is still intact, but we do have to show a few ions in solution. Okay. Strong bases, like the strong acids, dissociate 100%, and weak bases, like the weak acids, dissociate much less. Okay. Buffers, their main function is just to maintain the pH constant at whatever value you set that up. We can make a buffer solution for the whole range of the pH scale. Okay. Some examples of pH of soft drinks. You can see it's pretty acidic. This could be a problem, right? Enamel erosion due to the acidity. Right. Okay, which brings us to the solubility rules. Now, the solubility rules are a function of temperature, and the rules apply for a temperature of water at 25 degrees, because we know, or maybe you don't know, but you can adjust solubility of anything by what? Heating it up. If something doesn't dissolve, you heat it up and you get more of it in solution. Okay, so 25 degrees. Okay, now with respect to it being defined, and we're talking about ionic compounds here, if it's defined as soluble, then 100% of it dissolves completely. You go 100% into ionic form. Okay, and we designate AQ as its physical state, because we're talking about an ionic compound in water, which makes it an aqueous solution. If it is insoluble, its physical state is the letter S for a solid. Okay. Now, a very small percentage dissolves for this insoluble species. Very small percentage. And therefore, we have to write them together and not separate into the ions. So how's that table work? Okay, well, we have two columns here. One from column A, one from column B. Okay, column A right here. This is the soluble column. I'm going to split it right down the middle here. Okay. Now, number one, lithium, potassium, ammonium, and the ammonium ions. I call these guys the big four. Help you remember the big four there. Okay. Regardless of what they are bonded to, any anion, they are classified as soluble. So it could be lithium, anything soluble, sodium, anything soluble. The same with potassium and ammonium. Okay, the big four. The acetate ion that came from acetic acid, the acetate. Any cation, notice it is an anion. So any cation, any positive charged species, regardless of what it is, if it's copper acetate, strontium acetate, whatever, gold acetate, nickel acetate, etc., any metal, when bonded to acetate, it is soluble. Okay. The nitrate ion, similar situation. Okay. Any cation, any metal attached to the nitrate ion, it is classified as soluble. The halides, specifically chloride, bromine, iodine. Okay. Every cation bonded to these three ions is soluble, except when those halogens are bonded to these big metals, silver, mercury, or lead. Okay. If they're bonded to any of those three metals, it is insoluble. The sulfate ion, SO3, soluble with everybody, except if it's calcium sulfate, strontium sulfate, barium sulfate, silver sulfate, and lead sulfate. 1, 2, 3, 4, 5. There are only 5 sulfate compounds that are insoluble. There are only 3 halide compounds that are insoluble. That means everything else is soluble. Okay. So next column on the far right, this is the insoluble column. So by referring to that, it says everybody in that right column is insoluble. Okay. So let's take the carbonate ion. Carbonate ion, regardless of who it is bonded to, it is classified as insoluble, except when it's bonded to the big four. So lithium carbonate, sodium carbonate, potassium carbonate, ammonium carbonate, guess what? Soluble. Everything else insoluble. Chromate ion. Again, heavy metal, anything bonded to the chromate ion is insoluble, except, you guess, if it's bonded to the big four. Those 4 chromate molecules are soluble. Everything else in the world to date is insoluble. Phosphate, again, phosphates are insoluble, except with the big four. There's only 4 phosphates that are soluble in water. All the rest of them are insoluble. And we do it again. The sulfides are insoluble, but this time, unless they're bonded to the 4 and 3 more. If they're bonded to calcium sulfide, strontium sulfide, or barium sulfide, they are all soluble. So there are 7 examples of soluble sulfides, which means that all the other metals bonded to sulfide are insoluble. And the same is true with the hydroxides. Again, that's why I said sodium hydroxide is strong electrolyte, because all hydroxides are insoluble except when they're bonded to the big four and bonded to calcium, strontium, and barium. So we got 7 hydroxide examples that are soluble, and everybody else is insoluble. So copper hydroxide, insoluble. Lead hydroxide, definitely insoluble. Those leads are always pretty much insoluble unless they're bonded to nitrates. Okay, so that's how that works. Now, if we look at some examples here, let me clear the table here. We got, you have to know the name, right? You have to know what you're working with. This is Na2S. S is simply sulfide, okay? And so we go to the sulfide area, which is right here. And you might think, okay, insoluble, because it belongs in, it's in the insoluble column. However, guess what? You got sodium, and guess what? The big four. So this guy, sodium sulfide, will be soluble, and hence we use AQ. In fact, just remember, anytime you see sodium whatever, potassium whatever, lithium whatever, and ammonium whatever, those are soluble. Okay, look at, let me clear the table here. We have aluminum hydroxide. All right, so we look at the hydroxides. They are in the insoluble column, and we're dealing with aluminum. Well, there are only 7 examples of aluminum that are soluble. There's 4 of them, and there's the other 3, and none of them are aluminum. So guess what? Aluminum sulfide is insoluble, and hence we write the letter S. Now, it doesn't mean that it's totally insoluble. Remember, keep in mind, it's weakly soluble, very weakly soluble. A little bit of the ions do go in solution. Okay, silver bromide, we go to the halides. That's the bromide, okay? Normally the bromides are soluble except when you're dealing with silver. So silver bromide is definitely insoluble. Then we got calcium carbonate. We go to the carbonate column, which is the insoluble column. It is not none of the 4, the big 4, calcium is not. So therefore calcium carbonate is insoluble. Use F. That's what you see around, ring around the tub, if you have any, or around the faucet handles and so forth. Then finally, we have potassium. You don't have to go any further. The fact you see potassium first brings you over here. Always soluble. Okay, and so that is soluble. If we were to now write these things with, let's say, a beaker, obviously we will put at least 1 set of ions in solution and 3 hydroxides, and then the bulk of it is down here at the bottom, okay? Silver bromide the same way, silver ion, 1 set at least, and then the bulk of it at the bottom is silver bromide. And again, calcium carbonates, similar situation. At least 1 set of ions in solution, and then down at the bottom it's solid, would be solid calcium carbonate. All the other guys here, all totally 100%, they're all totally dissociated, okay? We got 2 sodium ions here and 1 sulfide. Don't forget the charges on your ions. Okay. Electrolytes, again, electrolytes, as I mentioned earlier, are nothing more than elements that have lost or gained electrons to form cations. So strong electrolytes, okay, that means they're good conductors of electricity. A pure water does not conduct any electricity. Ions in the water are the ones that conduct electricity. If you have soluble ionic compounds, been defined as soluble due to the solubility rules, or the strong acids, or a strong base, these guys are strong electrolytes, okay, and good conductors of electricity. Non-electrolytes are basically covalent compounds, with the exception of acids. HCl is a covalent compound, but because it's an acid, it does dissociate. So all the other covalent compounds, when they're placed in water, they do not dissociate. Remember, covalent compounds share electrons compared to ionic compounds that actually don't share. They're just brought together by electrostatic attraction, and they dissociate fairly readily. Okay, and those guys that are classified as weak electrolytes, those are weak acids, weak bases. Okay, anything that's classified as insoluble ionic compounds. So this summarizes everything for you. Okay, and where which compounds belong to which. And which brings us to this table here. Now, what do I mean? Well, if their electrolytes are gonna conduct electricity, so this depicts a circuit which is closed because the ions carry the charge, okay? And this here depicts non-electrolytes that cannot carry the charge. So, you know, it's like turning the light switch off. You have no current running through your circuit. The top one represents the ions represent the switch being flipped on, so you can conduct electricity. You know, you can think about, don't do this at home. You know, if you had a bathtub cleaned out real well, and you added deionized water, that's water with no ions, and you fill that tub up, and then you throw in your hair dryer plugged in, nothing's going to happen. No electricity is going to be happening. Let's say you're in there, you won't get electrocuted. Okay, at least not right away. Why not right away? Because as you're in the tub, you have on your body all kinds of salts and electrolytes, and they get dissolved. Now you have a current problem. You need to get out of that tub. But initially, you're good to go, because pure water has no ions to conduct electricity. All right. Images here. I think we've gone through that. Magnesium hydroxide shows it. You know, we know it's a weak electrolyte because of its insolubility. CH4, basically just a covalent compound, right? Covalent compounds, I repeat, do not break down to form the ions. I see that a lot, where they take CH4 or any covalent compound and they break it down. It doesn't happen that way. Remember, they share electrons. Okay? And potassium hydroxide, it's an ionic compound, plus the potassium up front is very soluble, and it's totally makes for a strong electrolyte. Okay. Now, how does this come into play with respect to looking at the compounds and determining whether it's strong, weak, or non-electrolyte? Well, let's go through each one. Okay, so we have a barium sulfide. Barium sulfide. Well, what we got to do is go through the solubility table, and you'll see that the sulfides, barium sulfide, is soluble. Classified as soluble means that it is a strong electrolyte. Okay, silver chloride, very similar. I think we did silver bromide. It shows, so this would be soluble, so I would say AQ there. This would be solid because it's classified as insoluble, which then makes it weak. Okay, again, I can overemphasize, even though it's classified as insoluble, we still have a small amount of ions in solution, which make it a weak electrolyte. Potassium, you don't have to go any further. You saw potassium first thing written. It is very soluble and makes it a strong electrolyte. Okay, we got H2 up front. That should indicate maybe I got an acid. Okay, well, you go check your notes, you find that H2CO3 is a weak acid. But let me explain. If maybe you forgot this is carbonic acid. Well, think about the CO3 carbonate, right? But the carbonate with the -2 charge has its hydrogens put back on. That makes it an acid. So that helps you out to identify what this number 4 is. We have an acid, and you take the carbonate, take off the ATE, add the IC acid, and you have carbonic acid, which hopefully rings a bell and says, no, this is a weak acid, and therefore a weak electrolyte, and 1 to 5% of it is dissociated, okay? Carbon dioxide, you know, is a covalent compound, and therefore will not dissociate any further. It stays intact. So it is a non-electrolyte because there are no charges there. Number 6, sodium. Don't need to go any further. It could be sodium, anything. Just by the fact that it is sodium, plus the fact that we told you it is a strong base, makes for a strong electrolyte, okay? Calcium carbonate, if we look, we did that one. We found out that it's classified as insoluble. So here we have aqueous, and we have solid here. Okay, for calcium carbonate, makes it insoluble. It's insoluble, makes it a weak electrolyte. Then number 8, you know, we have C6, H12, O6. It can be anything, but the point here is there's no metal involved. So it's not ionic, and so it must be covalent, and it's not an acid because we would have put H in front of the carbon. And so it's basically a covalent compound, which means that it is a non-electrolyte. All right, now sodium, number 9. Sodium, part of the big 4. Don't have to go any further. Very soluble, strong electrolyte. And then lead. Anytime you see lead, yeah, kind of lean toward insoluble. Okay, because leads, heavy metals tend to make things insoluble. Okay, this is AQ here. So if we look up lead sulfate, we'll find it to be insoluble, which then makes it into a weak electrolyte. Okay. All right. So that's basically how to look at it. If you're given an acid, then look at your list of acids we gave you, whether it's a weak acid or a strong acid. If it's a base, you can also look it up on the solubility rules. And if it's in the solubility rules, it's soluble, it's strong. Okay. All right, we gave you potassium hydroxide and sodium hydroxide and said those are strong acids. Well, that's fine. You can memorize that, but you can just use the solubility rule and realize that sodium is part of the big 4. Soluble makes it a strong electrolyte, which is itself makes it into a strong base because it has hydroxide. Okay. Any questions so far? Because, ladies and gentlemen, we are done with chapter 9. And I don't think I'm going to continue with, we've only a few minutes left, continue with chapter, next chapter. I'll start that up on Tuesday. Unless you have questions for 7, 8, 9, given that Tuesday is the exam. Okay.